Ma'am, I think we
Yes,
are waiting for a few participants to join, ma'am.
okay, no problem.
Yes, ma'am. Good afternoon, ma'am. Devika ma'am, have you joined, ma'am?
Hello, ma'am.
Yes,
Yeah,
ma'am.
I have joined, ma'am.
Yes.
Guest
Shall,
has joined me.
yes, ma'am. Yes, ma'am. Shall we start, ma'am?
Ma'am is there?
Yeah, I'm
Yes,
here.
ma'am.
Shiva, ma'am. Dr.
Yeah,
Shiva,
ma'am.
ma'am.
Yeah, ma'am, I am here, ma'am. I joined.
Yeah. Welcome you, ma'am. Welcome, ma'am.
Yeah, welcome.
Thank you.
Thank you.
Yes.
Yes. Shall we start the session, ma'am?
Yeah, ma'am, we can start.
Okay, ma'am. Thank you, ma'am. Usha, ma'am, please press.
Yes.
Venkatesh, sir. Usha, ma'am, please.
Good afternoon, everybody.
Yeah.
Hearty welcome to all the participants for this 5 days faculty development program. On behalf of our college management, principal, and all the faculty members, I welcome all the senior professors, faculty members from various colleges, and Mohamed Sathak AJ College of Engineering Fraternity. By the grace of God, we now start the first day FDP on cryptography and its applications. We expect your active participants, and inquisitive discussions as we embark on this journey together to delve into the fascinating world of securing information through cryptographic techniques. Now, I request Dr. Devi Kala ma'am, Professor, Department of Triple E, Head Student Affairs, to deliver welcome address.
A very good afternoon to one and all present here. I'm Dr. Devikala, Professor to be Department, Head Student Affairs. I feel proud and honored to welcome you all for this 5 days faculty development program on cryptography and its application. I would like to welcome our principal and our faculty members. Faculty development program is to enrich the knowledge of faculty by continuous interaction with academic and industries. So today we have a very special guest and speaker, Dr. Sheema Ramesh ma'am. Welcome you ma'am.
Welcome,
And
ma'am. Thank you.
participants are the major backbone for the success of every event. So I like to welcome all the participants who have joined today. Welcome you all. And last but not the least, I would like to thank and welcome our management, faculties, committee members, Mrs. Jabawala ma'am, Mrs. Usha ma'am, and Mr. Venkatesh sir for their continuous support to bringing up this faculty development program on today's platform. So I can assure all the participants the sessions will be more effective and useful. Kindly make use of it. And once again, I welcome each and everyone. Thank you.
Thank you, ma'am. Thank you for the warm greeting. I'm glad to introduce our speaker now to all of you. Dr. Sheema Ramesh Maniat, our speaker of the 5 days FDP, is a persistent, persevering, and pleasant personality with strong understanding in latest developments like machine learning, deep learning, and artificial neural networks. She started her schooling in Kerala State Board, completed her UG in ECE under Kannur University, PG in Embedded Systems under Amrita University. Under VIT University, she got her PhD in Information Security. Her contribution in teaching electronics and communication started in Malabar Institute of Technology, Kannur University, Kerala in 2011. Gagan Institute of Technology and Management, MDU University, Haryana in 2012. Rajiv Gandhi Institute of Technology, Bangalore in 2013. Since 2014, she has been working as an assistant professor at MBV College of Engineering, Whitefield, Bangalore. She has 13 years of experience in handling many subjects of electronics and communication. She has completed many courses related to neural networks, cryptology, machine learning using MATLAB, artificial intelligence, and many important current journals. She has published many innovative papers in national and international journals. Now I invite our speaker to deliver her speech on robust and lightweight image encryption approach using elliptic curve cryptology.
Thank you, ma'am.
Over to you,
Thank
ma'am.
you. Yeah, thank you,
Yes.
ma'am. Thank you for
Yes.
introducing me. Yeah. So before starting, I would like to give thanks to Dr. Mitlesh sir and the Race Mighty Square and for guiding me Federal University of Santa Maria, Brazil, for my postdoctoral fellowship as my guide. And thanks to Mohamed Sathak College also for taking me as one of the resource person to this 5 days FD. My screen is visible now. Shall I start?
Yes, ma'am. You can start.
Yes, ma'am.
I think.
Any disturbance is there, ma'am? Yeah, I think.
No, ma'am. No, ma'am. You can start, ma'am.
So, good afternoon and all present here. So yeah, this one. Yes, ma'am. Any? Shall I start?
Yes, ma'am, but your
Yeah.
screen is not visible, ma'am.
Screen is not visible.
Yes, ma'am.
Now, ma'am, is it okay?
Yes, ma'am.
Okay. Okay. So good afternoon, honorable present here. So for today, for the day 1, 5 day FDP for virtual FDP on cryptography and its application for the day 1, I would like to deliver my one of my work on cryptography, that is robust and lightweight image encryption approach using elliptical cryptography. So so before starting, I would just like to tell something like regarding cryptography. If anyone is already working or already worked on cryptography, if you have any suggestions to add in this, you can tell. And any doubts or any clarity if you want in my work or any code related any doubt also, you can share. You can ask me during question and answer session. So this is going to the my presentation agenda. So I will be giving you introduction, related work, proposed system with implementation, and the result and discussion also related to this work I would like to share, and even the future research direction also with reference. So as I think many of you know what is cryptography, right? So in cryptography means actually what we are doing, we are encrypting some data with some secret key. And okay, then the same thing, if we are sending to the receiver, receiver has to decrypt it, yes, with the same secret key for the purposes, right? So the biggest challenge actually what we are facing in image encryption is like how to design a lightweight cryptographic scheme. Lightweight in the sense like without any more complex mathematical expressions, okay, without increasing any computational burden, okay, with increasing number of encryptions. So encrypted image actually should have a high degree of imperceptibility. The sense like once we encrypt an image, okay, with secret key, okay, the encrypted image should not be no information should be there in the encrypted image. So the attacker or the third person won't be able to get any kind of information from the data. So it should have a high degree of imperceptibility. And the next thing is like image should have retain maximum level of this information while performing reconstruction operation. After decryption, the decrypted image should be same, or it should retain all the information, okay, what is present in the input image. So this and all we have to make sure while doing any encryption algorithm, and it should be fast. The response should be fast. If you're taking one day or there's more than 24 hours to encrypt and decrypt one data, means that won't be any use, right? Because you want to do any emergency purpose, you want to encrypt any image or data or any information, means it should have within a fraction of second or minimum 1 or 2 minutes also fine. So this is what my agenda. It should have within less time, and should have a high degree of imperceptibility, and the reconstructed image should have maximum level of informations with respect to the input image. So I try to try to include all these aspects in my all the works. So my proposed system contribute all essential security demands required in a robust image encryption mechanism for the optimal image security. So this is my related work before starting this method. Okay, so I mainly gone through the chaotic map or chaotic image encryption is another type of image encryption, like electric curve cryptography. So why I have chosen chaotic map is I just want to compare to chaotic map how better is ECC, electric curve cryptography. So I have referred a few papers. These are the papers which I referred, and so what I have observed in all this works, okay, all this work is chaotic cryptography is good actually. It is having a lot of advantages, but as compared to ECC, that is what my problem description. Compared to ECC, or after reviewing all its existing approaches, what I have observed is chaotic map is predominantly used in many image scrambling technique. But whereas the encryption mechanism discussed is quite complex actually. It is like mathematical expressions are more little complex compared to ECC. So the major pitfalls or major the drawbacks, what you have to analyze in this all this work is increasing computational complexity with high iterative steps of encryption. So that also will take lot of time. If you're having more complexity and more number of steps are there, that will create a lot of issue while decryption process, and even lack of evidence of similar security performance on different forms of images, and even the trade-off between the image quality and security demands. And another thing is doesn't ensure optimal image imperceptibility. Like after decrypting, okay, after encryption also, you can see the encrypted image contain lot of information from the input image. So the attacker or the third person can easily capture all the information. So there is no use of encrypting by using such kind of algorithm. Right. So these are all the major pitfalls I identified after referring this many papers. So it is also found that there is a less exploration of many other standard cryptographic techniques in image encryption processes. So therefore, the problem statement is what actually how to construct a novel, a robust image encryption process that not only offer cost-effective encryption scheme but also should retain maximum level of image imperceptibility. So this is my proposed methodology. So I think the block diagram is visible to all. So here the implementation of the proposed image encryption is mainly carried out by using this analytical research methodology. So what do you mean by analytical? Analytical research methodology. So it is shown here. Okay. So main proposed system performs actually here you can see this is my input image. Okay. So what I have done here step by step I'll just tell you. This is my elliptic curve encryption. This is my input image. Okay. So in the input image, suppose my input image is of size of 256 cross 256. Okay. So what I have done means I have taken a group of n number of pixels. Okay. Followed by computation of public key. So we need a public key and private key for any kind of encryption, right? So here I am developing a public key. Okay, the public key with the help of the input image. The input image I have done the grouping system such a way that n number of pixels. That n can be any number. So till 10. 10 number of pixels I have taken. Okay, I have computed by using 10 number of pixels by with the help of elliptic curve cryptography. I have developed a public key here. Okay, the public key is my 10 group of pixels that will act as a public key to do elliptic curve cryptography. Okay. Now in elliptic curve cryptography, actually we have learned what is point addition. So point addition is used here. Okay, after elliptic curve cryptography, point addition is used to degroup the pixels. So whatever I have grouped here, first I'll group it and I'll do the elliptic curve cryptography here. The results after getting, I'll degroup it back. Okay, degroup it back, and I'll rearrange it in the form of again a n cross n image or 56 cross 56. So here I'll be getting a different image now. Okay, one level of first level of encryption is done here. Primary encryption is done here after grouping and doing elliptic curve cryptography. So I'm doing point by point addition here. Okay, so after that, with the help of DNA cryptography, the DNA is deoxyribonucleic acid. We all know it is a unique thing present in our human body, right? So I am using DNA as another second secret key to encrypt my second level of encryption. So DNA is having 4 nitrogen bases, that is adenine, thymine, guanine, and cytosine. Here you can see ACTG. Okay. So why using DNA digital coding technology? What is DNA digital coding technology? It's adenine, thymine, cytosine, and guanine. ATCG. Okay. We are coding with some binary like A00, T is 11, like that. A00, T11. Okay. C can be 10, G can be 01, like that. Okay. Vice versa. So this, by using this technology, okay, what I have done is each pixel is having 8 bit, right? Each 8 bit I'm converting into DNA. DNA matrix. DNA matrix is by using DNA digital coding technology, I've converted each pixels in the form of ACTG. ACTG is having binary values 00, 01, 101. Okay, that matrix. Okay, I'm just calling as my DNA matrix. This is my DNA matrix. Okay, so now once I got the DNA matrix, okay, DNA matrix I am dividing into 3. Not dividing, in the same matrix I'm considering as matrix 1, matrix 2, matrix 3. Okay, which can be used for further scrambling. So first matrix is my first DNA matrix that I am just flipping it, just taking 90 degree. Okay, again one more 90 degree. So 90 degree flipping, like just I'm putting 90 degree shifting. Okay, so that's why I have put in yellow color. Yellow color first will come here, then here, then here. So this is matrix flipping have done here. So I have three matrix now. Let it be B1 or A1, A2, A3. Okay. This A1, A2, A3 is used for bit XOR. So the scrambling is performed on encrypted images followed by bitwise XOR operation. Okay, in order to obtain the final. So what I have done means this image, okay, as bit XORed with the previous image. After here we get one image, right? That is bit XORed. That result is bit XORed with second one. Again bit XORed with third one. Okay, that is finally scrambled. Okay, scrambling means just rearranging of pixel, mixing of pixel value. Okay, after that, finally, I'm getting the encoded image. This is just the analytical approach of my proposed algorithm. So I'll tell you step by step what has happened in the algorithm. Okay. So after this, just put the algorithm implementation. Same thing what I told, just in the form of as an algorithm. Just I will tell you in a brief. Primary encryption is a secondary encryption, as I told. So this is a primary encryption. Okay, this part primary encryption, and this part is a secondary encryption. Fine. In primary encryption, what I had done is I have generated first all the secret key. I need K1, K2, G, okay, PB, and what will these all are the some random number, okay, which I need to transmit through the which I have to transmit from transmitter side to receiver side. Okay, so algorithm initiate by executing or by defining a random number K1, K2 for transmitter and receiver. This random number K2 which is used first. K2 is also used for computing the public key. So I need a public key here which is known as PB. So PB is obtained from K2. Okay, which is a product of K2 and G. So K2 into G will give the PB. Okay, this all calculation is not done by me. This is coming in elliptic curve algorithm. Okay, this elliptic curve algorithm calculation is along with that I have done my own algorithm here. So I combined both and proposed my method actually. So the dimension of the image, let it be I, if that is n cross m. Okay, so that first I am converting into a double precision. In the sense, I convert each like my input image into a double precision image. Okay, after that, what I have done is I have taken the grouping of pixel I told, right? So I have taken n number of pixels. Okay, I convert into a precision integer. So I called a function f1, which is applied for transforming the base to variable precision integer. So each pixel, like a grouping means I'm converting into a fixed integer value. 10 pixel I'm taking, converting the fixed integer value. Okay, this fixed integer value I'm storing in one variable int. Okay, this one I have given to elliptic curve cryptography for point addition actually. So all the input output of the int means after converting into a precision integer is appended in order to obtain what PM. All I'm appending together. I'm getting a PM. What is PM? PM is my another secret key actually. So, okay, so I need this number K1, K2, G, PB, N, PM. These all are my secret key actually. This and all are generated by the sender or the person who want to do this encryption algorithm. Okay, so this secret key will be known by me only. I'm not sharing this to anyone. So this secret key. So next part actually, what after getting this many secret key, next part of the algorithm is to compute a secret key one more KPB. Okay, KPB. What is the role of KPB here? KPB is obtained as a product of the initial random number K1, okay, and the public key PB. So KPB also is having another role here in encryption. Okay, so this after getting all those things, I had to construct a matrix H. Okay, that represents the value of 3 points on electrical curve cryptography. In electrical cryptography, we know it is having a 3 points in the coordinates. Okay, once we get the 3 points, suppose it A, P, B are the 3 points I'm using here. Okay, so what will happen? The function G is applied that represents the standard elliptical curve with input arguments of secret key KPB and the matrix H actually. So when the function G, okay, the G which what you're applying here, G is applied that represents the standard elliptical curve with input arguments of secret key KPB and the matrix H. This all are will like this all is followed by applying a function known as GADD. What is GADD is doing? GADD is mainly represent the elliptic point addition. Okay, the addition point on the operation of elliptic curve. Considering all these input arguments, okay, because to do this elliptic curve addition, I need all these secret points. So that's what X1, then YPM, then KPB, YKPB H. This, after getting all this, I'll do the elliptic additions. Okay, and finally, these operations will lead to the output of the ciphertext CT. CT is my final ciphertext which I got. Okay, which is first subject to the another inverse function of function F2 that converts after getting my CT. I have done here integer conversion. I will do the reverse of that. That is variable that convert the variable precision integer to the base file. First I did base to integer. Now integer to base I am doing for the crypto to get the reverse process. Okay, so this up to here is my primary stage. Actually. Primary encryption I can say. Okay, so in case the length of the while doing all this, if my length is not matching up to the matrix length, means I can append n number of zeros. Okay, to get the size same. Okay, that option we can do. So that will not take or that will not affect my information. My what is information what I have done in my data. Okay, it will not remove my any of the information. So finally, the obtained primary encrypted image I'm calling as I prime. I prime. Okay, encrypted. This is done by using elliptic cryptography. Now in the secondary algorithm, secondary encryption, what all things is happening is first step of the algorithm is to perform the reshaping. I have to reshape my image. Okay, the primary encrypted image what I got, I'm reshaping here. After that, what I'll do, I'll extract the number of rows and column, how many rows and columns are there, I have to extract. Next step of algorithm is to generate a nucleotide sequence. That is nucleotide sequence is DNA sequence. As I told, adenine, thymine, cytosine, guanine are the 4 nitrogen present here by using ATCG. Okay, we are generating a DNA matrix here. So that I'm calling as DMAT. So what is DMAT? DMAT is my DNA matrix. Okay, by nucleotide sequence. Okay, then what I am doing is I will do some permutation and combinations. Okay, like just to just I'll mix all the pixels. Okay, just to get a confused image. Once again, get a confused image. That image, okay, I am calling as B1. Then the transpose, DMAT transpose, I'm calling as B2. Just transpose, just I'm shifting dynamically. Again, flipping. B3 is a flip of DMAT. Again, flipping it. Okay, so 3 times I'm like 3 DNA matrix I'm getting B1, B2, B3, which is a original DNA matrix. The transpose of the previous one, then the flipped of the previous. So like that, I will get B1, B2, B3. Okay. Now what I'm doing is my new encrypted image A2 is equal to A1 bit XOR B. What is A1? A1 is the previous image which I got from here, the primary encrypted image. A1 bit XOR with B1. Okay, that is A2. Then that A2 bit XOR with B2. B2 is this one, and A3 bit XOR with B3. So this is a 3 type of bit XOR operation I'm doing here. And finally, what I'm obtaining is my the final encrypted image which I'm calling as ISCC-ENC. Okay, that is my A4. This is how we have done here. So after doing this one, because I have done a 2 level of encryption. So one is one with elliptical cryptography, and that is given to DNA matrix. And with the help of DNA encryption, I am doing second level of encryption. Okay. So these are the result which I got actually here. So you can see original image, encrypted image, the decrypted image. So on original and decrypted image should be exactly ditto without any loss of information. And from the encrypted image, you won't be able to identify any of the information of this input. Okay. So here we can see the comparative analysis. Every algorithm, whatever the work you're doing in the research, we have to compare, right? We have to do the comparative analysis, and we have to prove that our algorithm is better. It's giving better results. So in order to assess an effectiveness factor associated with the proposed image encryption scheme, necessary to evaluate the outcome of the image imperceptibility. How strong our algorithm is, right? So outcome of the decrypted image can only be called as imperceptible if it bears nearly similar or closer value of signal quality with the original image. So that it is very hard to differentiate the signal quality of the decrypted image. So whatever image you got, we have to feel like, okay, our image is very strong, and it should be difficult to identify which is the original image, it's a decrypted image. That way we have to show. So that is the main outcome. Okay. So moreover, the best mechanism to prove that the proposed encryption method offer potential security without hampering the signal quality. Okay. And we have to judge one more thing, the peak signal to noise PSNR. Okay. So some sample visual outcomes of the proposed systems are highlighted here. Okay. Here, this is the correlation coefficient analysis. What is the correlation coefficient analysis? This analysis will tell how strong your encryption algorithm is. Okay. And here what you can see is the visual outcomes of the gray scale as well as color scale image. Okay. Both gray scale also taken and color scale both have done here. Black and white and even color image. Okay. The both outcomes you can see here from this. And also there is no significant difference in the visual outcomes for any forms and the type of image. Okay. And hence the proposed system can be used widely for encrypting any type of image actually. And for effective analysis, what we can say, the coercion coefficient analysis, I have compared with one of the paper done by Singh and Singh. Okay, I have referred here the reference here. So according to existing system approach of Singh, okay, the pixels are actually, you can see his result and our result. Okay, what you can see here, the the pixels are grouped followed by the calculation of public key using elliptical cryptography. So here this red dot represents a correlation analysis of the encrypted image, and the blue is a correlation analysis of input image. So what you can see, input image pixels are very much correlated. So that's why you are getting a straight line. Okay. Yeah, but in the case of encrypted image, it should be scattered. Okay. But if you compare it with the existing Sing and Sing work and our work, you can see here our the pixel, how the correlation coefficient is, it is like fully evenly shattered, right? So what we can say, according to system, like what we can say, the pixels are grouped followed by calculation of public key system in elliptical crypto system. The point addition is performed on public key followed by degrouping of the encoded image, and finally all the values are rearranged in order to obtain the encoded image, right? That's what we have done. We have done first grouping, then we are degrouping, and finally we rearrange to get an encrypted image. So our technique secured against image tampering attack, and also definitely it is not resistive against the statistical attack that has a possibility of breaking the encryption actually. So what we can say is the Singh, the proposed work of Singh, okay, is then improved compared to his work. Our work, we have added, along with elliptical cryptography, we have added nucleotide sequence process, DNA encryption also. Okay, so compared to this work, our is having double encryption, actually 2000 encryption we have done. Okay, and we are getting a better result compared to this Sing work actually, Sing and Sing work. Okay, and what the table here highlights is the correlation map for the proposed and existing in all three metrics direction. You can see here the interference of the correlation map, okay, proves the proposed system offers better encryption scheme in correlation value of any of the direction of the proposed system, okay, is quite low as comparison to the existing system of C. So we verify this outcome considering the colored image also, not only for grayscale image, even the color image also we have considered. Okay, so next is just I want to show that for the color image also. So here you can see horizontal pixel projection, vertical and diagonal. So what actually this being horizontal, vertical and diagonal in the sense, we have taken here also all the three I have mentioned here. We have taken random pixels of both input image as well as encoded image through horizontally, vertically and diagonally. Okay, then we have projected with the help of correlation coefficient analysis. So this way we got three different graph, okay, with the horizontal pixel projection, vertical pixel projection and diagonal pixel projection, and all the three are giving a better results compared to the other works. Okay, so further effective analysis, what we have done is we have performed the comparative analysis of the proposed system. In the comparative analysis of the proposed system with respect to PSR, peak signal to noise ratio, okay, and number of changing pixel rate, that is NPCR, and unified average changing intensity, UACI. So these are the main evaluation parameter. Okay, we have to do every encryption algorithm. So the standard has some standard value also. For NPCR value, it should be near to 99%. Then we can say our algorithm is best compared to the existing. And even UACI should be near to 33%. Okay, and PSNR value, peak signal to noise ratio, we have to show that it is comparatively high compared to the previous. Okay, so it should be more actually PSNR. So if you see this comparative analysis, okay, a closer look into this comparative analysis shows that the proposed system offers better performance in contrast to the existing system. So I have referred by Singh and Singh paper because his work is almost similar to our work. Like ECC they have done, but DNA cryptography is not that. But his results, his value is for UACI is less actually. In an episode is less actually. 73% like shows that it's very easy for the attacker to attack this algorithm. Okay, it can break the algorithm, and even USA should be near to 33, 32. So that way we can prove that our proposed method is good compared to the existing. Fine. So so what actually we have observed here means performing an image encryption is not only implementing the cryptographic algorithm, okay, to cipher the image, but also we have to take care. We have to make sure that the image should retain the maximum information after, because after decryption also there won't be any loss of information, okay, in the decrypted image. So it should retain maximum information, and the signal quality should be good actually, and we have to make it little fast. Don't take 1 hour 2 hour encryption process and decryption another 1 hour. Okay, so it should be within a minutes, or it can be a fraction of second depending upon the algorithm. And lower computational resource dependencies. If you're depending more resources, then it will be more complicated. So better with lower resource dependence, like lightweight, with the less number of time, and with a good signal quality. Whether we can do our any image encryption algorithm, and that is meeting our all requirements like NPCR, UACI, PSNR, entropy, and all, like correlation coefficient analysis, histogram analysis, then we can say our algorithm is better compared to others. So, and we should ensure both forward and backward secrecy. So it should be like whatever you're doing in the forward, in the sense the encryption process, same way we have to able to do the decryption process, so both forward and backward secrecy. So this way we can say our proposed system implements on such technique and bears almost all the criteria what we have explained right now. Okay, and apart from that, it also exhibit faster computation. Okay, and it can be utilized for encrypting large number of images, as well as it also possible for any form of image, that not only black and white or grayscale. It can be taken for color images also. Okay, and also it introduces novelty from all existing approaches by incorporating an extremely lightweight encryption technique. Not only maintains good pixel integrity, also it offers faster computation also. Okay, so with this, with the retention of good signal quality, the proposed system can also be used in encryption of medical image or a forensic file that bear potentially informative content. So, not only for normal images, okay, it can be used for any medical images or any forensic file, okay, or any other military applications or any other aeronautic, any applications we can use this algorithm actually. So these are a few of my reference, and even I would like to show my results also, like MATLAB result. So this is my code for this algorithm, and they have taken this as my input image, and I got encrypted image like this. It's a purely encrypted image. Okay, and this is a result which I got: original image, encrypted image, and decrypted image. And these are my analysis: horizontal pixel projection, and this is my vertical, horizontal, vertical. So here you can see pixel distribution is good. Yeah, this is red for encrypted image and the blue for the original image. So input original image or input image pixel is like a straight line, because they are correlated to each other. Pixel values are correlated, highly correlated. But if you go for encryption image, it is fully uncorrelated, fully spreaded actually. And this is a diagonal image, horizontal, vertical, and diagonal. Okay. And if we go with the final results, here this is my final I got. I took some 61 seconds actually, but for my upcoming work, like tomorrow and after which I'm going to show, like I have taken very less number of seconds actually compared to this work, because maybe here I'm using two type of encryption. One is ECC, grouping of pixel I'm doing, then I'm converting into degrouping, then again converting. So maybe that step by step, it's take more time. So 61 second took, and the PSNR value I mentioned here. Yeah, SSIM. SSIM is structural similarity. Structural similarity is mainly tells about how much similar is your decrypted image and original image. So it should be near to 1. Near to 1 means both are same. So I got 0.9975. So it's near to 1 only. So my decrypted image and my original image are both are same. And peak signal to noise ratio, I got around 14.7. Okay. And the SSIM of the encrypted image is negative, should be negative, because there is no correlation between my encrypted image and original image. It's negative. I can't relate both. So negative value I'm getting. And correlation coefficient value, around horizontal value, I got 0.9. So correlation means how your original image is. So they are highly correlated to each other, because I told, like, here you can see they are highly correlated. The pixel values are correlated. That's why they're getting a straight line. So which means each value should be near to 1. So I'm getting near to 1. Okay, around horizontal of original image, and even vertical image also I'm getting near to 1, and diagonal image also I'm getting near to 1. Okay, but if you go with the encrypted image, that they are not at all correlated, so it should be less than 1. So I'm getting 0.027. Here I'm getting negative value. Okay, for a vertical encrypted image, and for diagonal I'm getting 0.01. So this way I can prove like this algorithm is giving a better results compared to the any existing work. And even NPCR value, I got 98%, and UAC I got 32 points. So that's 33, near to 33%. So with all these things, I can tell like my proposed this work is good compared to the existing one. Okay, so that's about this day one presentation about application of cryptography. So any doubt in this work or any suggestion, you can just tell. So tomorrow I would like to give again the application of cryptography only, based upon machine learning and neural network concept. So this is my the initial work which I have done, which I got published in an international conference that's on Scopus based only. So tomorrow I would like to share my second work, which is related to machine learning approach. Okay, then next day with deep learning, and one more with the machine learning. So I would like to compare all the works together, which is better. I have done analysis of all the works, and I would like to highlight which work is giving better results in cryptography field. So what do you, sir, ma'am, any doubt you have or any suggestions if you have in my work, you can give. Devikala, ma'am?
Hello, ma'am.
Yeah, yes, ma'am. Ma'am, that's over, ma'am, from my end. Any discussion or any question or answer session is there? I'm ready to answer,
Yeah,
ma'am.
let us check with our participants, ma'am.
Yeah.
Okay, dear participants, so any doubts or clarity if you require, other than this also, no problem, you can discuss with the ma'am. So you can raise your hand so that it can be muted. Let us wait for 2 minutes, ma'am.
Yeah, no problem.
Okay. So really, we had a wonderful session, ma'am. Your
Thank you.
your work is very nice. It's going on well.
Thank you.
So really, I think everyone have got some idea regarding this cryptography.
And that's what anyone is doing in this area, or they'll be having some suggestions, so they can put forward. If
Okay.
they want my PPT or code also, I'm ready to share actually, because I already published,
Sure.
so I don't have any problem in sharing. So,
Okay. So regarding this PPT, you can share, right? No issue.
yeah, no problem.
Okay, fine, ma'am. I think our faculties are
No
very
problem.
understood very well. So Usha, ma'am, you want to brief, ma'am?
Yes, ma'am. Ma'am, how about our photo session, ma'am?
Yes, we can take, ma'am.
So participants, can you please switch on your video for the photo session? Venkatesh sir?
Yes, ma'am.
Ma'am, I think Devika, ma'am, my video is on, I guess. Are you able to see me or not? Yes, ma'am. Hello, Devika, ma'am. You're not audible.
It's not visible, ma'am.
Okay, not visible.
Other participants, please switch on your video.
Is it coming, ma'am, now?
No, only a few images are coming, ma'am. We couldn't see you, ma'am.
Okay, okay.
Dr. Shiva, ma'am, it's not visible, ma'am.
Just time, ma'am.
Yes, ma'am. Venkatesh sir, can you take the screenshot, sir?
Okay, ma'am.
We request other participants also to switch on the video, please, for the photo session.
I think now I'm visible, ma'am.
Yes, ma'am.
Thank you.
Venkatesh, sir. Sir, are you ready, sir? Devi, ma'am, we couldn't hear you, ma'am. You have to unmute yourself.
Yes, ma'am. I have taken, ma'am.
Yes, sir.
Now
Yes,
only Shima ma'am have joined, sir.
yes, sir.
Participants, everyone, if you unmute, it will be nice, I think. So the session will be good. Okay, ma'am. Yeah, sir has taken, I think. You please
Yes.
tell
Okay.
that.
Yes.
Thank you. Thank you.
Thank you.
Thank you so much, ma'am.
Thank you to see everyone. Yes, sir. Thank you so much for the detailed explanation on robust lightweight image encryption approaches. You have given so many relevant references and images also, ma'am. Shima,
Yes.
ma'am, thank you so
Yes.
much, ma'am.
Oh, yes, ma'am. Thank you, ma'am. Thank you.
Thank you, participants, for being here with utmost interest. And let's make this learning experience enriching every day. We shall meet tomorrow, the same 2 o'clock, and have a nice day. Thank you. Thank you all. Thank you.
Thank you.
Thank you, ma'am. Thank you all the participants. Thank you, Dr. Ma'am.
Yeah. Thank you.
And thank you all the committee members. So we can leave now.
Thank you all.
Thank you, ma'am.